Welcome back everyone. In this section we will learn about thiols. Thiols are similar to alcohols with a difference that instead of oxygen they contain sulfur atom. Let's recall the structure or general structure of alcohol. So alcohols are denoted by ROH where R is a carbon chain. For example, this would be an example of alcohol. On the other hand, thiols are those compounds which contain SH group. As you can see the similarity now, in alcohols we have OH group and in thiols we have SH group. So therefore thiols are also known as thioalcohols. That's why the name thiols. An example of a thiol is shown here, and you can see that it is quite similar to the alcohol example I have drawn here. So therefore we can say that compounds containing the SH group bonded to a tetrahedral carbon or aromatic carbons are known as thiols. The SH group is often referred to as sulfhydryl group. The name of a thiol is assigned based on the number of carbon atoms in its chain, followed by the word thiol. For example, if a thiol contains only one carbon atom in the chain as shown here, then the name of this compound will be methane thiol because hydrocarbon with one carbon is known as methane. So in case of thiol, the name will be methane thiol. Similarly, if a thiol contains a carbon chain with two carbons, then its name will be ethane thiol because any alkane with two carbon is named as ethane. For thiols with three or more carbon atoms in its chain, a locator number will be needed to show the location of the sulfhydryl group. For example, if my thiol contains four carbon chain as shown here with the SH group at number 2 position from the right hand side, then the name of this thiol will be 2-butane thiol. The 2 is the locator number for SH or sulfhydryl group, and butane represents the length of the carbon chain in the thiol. Few examples of thiols with three carbon atoms are given here. So as we learned in previous slide that in case of thiols with three or more carbon atoms in its chain, the locator number is needed. So therefore example on the left hand side is named as 1-propane thiol, and the second example is named as 2-propane thiol. Thiols are known for their strong odors. For example, the distinct odor of cheddar cheese and garlic is due to the presence of methane thiol in them. Onions contain 1-propane thiol, which causes ice to water when an onion is cut. The unpleasant odor from the spray of a skunk is due to 3-methane 1-butane thiol. Ethane thiol is added to natural gas so leaks can be detected because natural gas is odorless. Let's name these simple thiols. In first example, we have a thiol with the 3-carbon chain and the sulfhydryl group is connected to the middle carbon. So when we number this, so the sulfhydryl group will be connected to number 2 carbon. So therefore, we'll use the locator number in the beginning. So that will be 2. And the name of thiol come from the length of the chain. For 3 carbon, the name would be propane. And then we will write thiol at the end. So the complete name will be 2-propane thiol. Similarly, in second example, the carbon chain is 7 carbon long, and thiol group, or the sulfhydryl group, is closer to the right hand side, so therefore we will number from the right hand side, and the locator number for SH group is at number 3. uh, so therefore name of this thiol will be 3 heptane thiol. And finally, in the third example, we have a thiol with a carbon chain which is 5 carbon long. So one carbon is here, and then we have 3 CH2 groups, and then we have another CH2 group here. So essentially this compound is CH3, CH2, CH2, CH2. So these 3 CH2 groups are shown here with this 3 subscript, and then another CH2, and then SH. So therefore this thiol is 1 pentane thiol. The ether functional group consists of an oxygen atom with a single bond to 2 carbon atoms. The R groups can be a carbon chain, ring, or a aromatic group. Examples of compounds with ether functional groups are shown here. In first example, the oxygen is connected to simple alkyl chains. On the other hand, in the second example, the oxygen is connected to a methyl group on one side, whereas it is connected to an aromatic ring on the other side. Ether functional group is widely distributed in nature, and it is present in many pharmaceutical compounds. The ball and stick models of ether compounds are shown here, and we can see here that the molecular geometry of oxygen atom present in ether functional group is bent. An ether is a relatively unreactive functional group. Therefore, those ethers which are liquid at room temperature, such as diethyl ether shown here, are often used as organic solvents. Organic solvents dissolve organic compounds but do not react with them. Ethers with a low molecular mass are volatile liquids, or they can also be gases, and some of them have found applications as anesthetics. So anesthetics are gases used to put patients to sleep during medical procedures. The first anesthetic was diethyl ether, which is also used as organic solvent. Modern anesthetics contain carbon and fluoride bonds instead of carbon and hydrogen bond. Example of modern anesthetics are shown here. These modern anesthetics are gases at room temperature, and they reach the brain faster than diethyl ether, causing the patients to go in and out of consciousness more rapidly. Patients under these anesthetics feel no pain and have no recollection of the procedure when they awaken. Ether functional group may look similar to alcohol, but it is quite simple to distinguish ethers from alcohols. Ethers have oxygen atom bonded to 2 carbon atoms. On the other hand, alcohol functional group has oxygen atom bonded to 1 carbon atom and 1 hydrogen atom. For example, let's take a look at the molecular structure of an antidepressant medicine, Effexor. Effexor contains both ether functional group as well as alcohol functional group. As we can see, here that in case of ether functional group, oxygen is connected to carbon in the methyl group as well as another carbon present in the benzene ring. However, in the alcohol functional group, oxygen is connected to hydrogen on one side and it is connected to carbon on the other side. Let's identify each of these compounds as an alcohol, phenol, thiol, or an ether. In example A, we have an OH group, that's a hydroxy group, which is an alcohol group, and oxygen is connected to hydrogen on one side and a carbon on the other side, so therefore this compound is an alcohol. In B, we have an oxygen atom. It is bonded to carbon on both sides. So because oxygen is linked to carbon atoms on both sides, so therefore this compound is an ether. In example C, again we have an oxygen atom which is bonded to hydrogen on one side and a carbon on the other side. So therefore this is again an uh, hydro may look like an alcohol, but because on this side the carbon where the oxygen is connected to is part of aromatic ring. So whenever an hydroxyl group is connected to an aromatic ring, then this entire unit uh, is known as a phenol. So this is an example of a phenol. In example D, again oxygen is connected to carbon in one side, which is a methyl group, and aromatic ring on the other side, so this is still an ether. Amines are class of organic compounds related to ammonia. A ball and stick model and Lewis structure of ammonia is shown here. In ammonia, a nitrogen atom is connected to 3 hydrogen atoms. Amines are formed when we replace one, two, or all 3 of these hydrogen atoms with alkyl chains. For example, in this example of amine, one of the hydrogen is replaced with a methyl group, or in other words, one hydrogen is replaced with one alkyl group. In the second example, 2 hydrogen groups atoms are replaced with alkyl groups, or in this case 2 methyl groups are present instead of hydrogen. And finally, in the third example, all 3 hydrogens of ammonia have been replaced with methyl groups. Instead of methyl group, we may have a longer alkyl group such as ethyl or even cyclo alkyl group or aromatic rings. All of these compounds in which hydrogens of ammonia is replaced with either alkyl chains, cyclic rings, or aromatic rings are classified as amines. Amines are subdivided into 3 classes depending on the number of R groups on the nitrogen. If nitrogen has only one R group, where R group represents a alkyl chain, a ring, or a cyclic compound, then the amine is known as a primary amine. So in other words, primary amines are those amines where only one hydrogen of ammonia is replaced by R group. Secondary amines are those amines where nitrogen is connected to 2 R groups, or 2 hydrogens have been replaced by alkyl chains or rings. And in tertiary amines, all the hydrogens of ammonia have been replaced by the alkyl chains, rings, or aromatic rings. For amines, we will learn the guidelines for common names of amines. We are not going to use IUPAC names of amines because common names are more readily used in case of amines. The common names of amines are based on the number and type of R groups on nitrogen. Each R group is named as an alkyl group and then it is followed by the term amine. For example, in this case, the alkyl group or the R group is methyl. Therefore, the name of this amine is methylamine. In the second example, we have two methyl groups connected to nitrogen. Therefore, this amine is known as dimethylamine. And finally, in this tertiary amine example, all three alkyl groups are methyl alkyl groups or methyl groups. So therefore, this amine is known as trimethylamine. One thing you would have noticed here is that in all of these examples, nitrogen is connected to methyl group. However, in many other amines, we may have different kind of alkyl groups. So, for example, nitrogen may be connected to methyl as well as ethyl group. And in this case, we will name it by writing the names of alkyl group in alphabetical order. So in this example, because one of the alkyl group is ethyl and the other one is methyl, so alphabetically we will write the ethyl first and then methyl, and then we'll write the amine at the end. So therefore, the name of this amine would be ethyl methylamine. Primary and secondary amines do have a nitrogen atom which is connected to hydrogen atom. Uh, this nitrogen and hydrogen bond gives primary and secondary amines ability to form hydrogen bonding. We know that hydrogen bonding is the strongest intermolecular force which results in primary and secondary amines to have high melting and boiling point. No such nitrogen and hydrogen bonding exists in tertiary amine because in case of tertiary amine, nitrogen is connected to three carbon uh, groups or carbon atoms or alkyl groups on all three sides. So nitrogen and hydrogen bond does not exist. So therefore, tertiary amines cannot form hydrogen bond, and hence tertiary amines have a relatively low boiling point as compared to primary and secondary amine. All of these amines, that is primary, secondary, and tertiary, can form hydrogen bonding with water. Hence, all of these amines will be soluble in water. Just like alcohols, if amines have alkyl group longer than 4 carbons, then they will not be soluble in water. So in other words, amines with small carbon chains or less number of alkyl groups will be soluble in water. Amine with more than 4 carbon atom chains will be insoluble in water. Amines listed below are structural isomers. Write a skeletal line structure for each and predict which amine has the lowest boiling point and why. Let's first write the skeletal line structure. So in case of example A, we have nitrogen atom connected to three uh, methyl groups. So this would be the skeletal line structure of uh, amine given here. In example B, we have nitrogen with an hydrogen bond and we have ethyl group on one side. So I'll use a zigzag notation for ethyl and then methyl group on right hand side. So that would be methyl. And finally, for example C, we have a propyl group or 3-carbon chain, and nitrogen does have 2 hydrogen atoms connected to. So let's make a propyl group on left hand side. So these 3 skeletal line structures are for the amines given to us. Now we need to predict which of these 3 molecules have the lowest boiling point, which of these 3 amines have lowest boiling point. So the answer is amine given in A is the one with lowest boiling point. The reason is amine in example A is a tertiary amine, and tertiary amines cannot form hydrogen bonding, therefore it has the lowest boiling point. Amine given in example B is a secondary amine, and example C is a primary amine. Both primary and secondary can form hydrogen bonds because they do have nitrogen and hydrogen bonds, and hence they will have higher boiling point as compared to the tertiary amine. Amines are responsible for the physiological activity of neurotransmitters and many other endogenous substances. Amines are also a key functional group in many pharmaceuticals. For example, the antidepressant Prozac relies on the secondary amine functional group for its activity. Amines derived from plants are known as alkaloids. Examples of some well-known pharmacological active alkaloids and their biological sources are shown here. The active ingredient in tobacco is nicotine, and as we can see that uh, the active functional group in nicotine is an amine. Similarly, cocaine, which is obtained from cocoa leaf, also relies on the amine functional group. Psilocybin, shown here, is an alkaloid produced by various species of mushroom and is known to have psychedelic properties. Identify the tertiary amine group in this molecule. Remember, tertiary amine group is an amine in which nitrogen is connected to 3 alkyl uh, groups or rings or aromatic rings. In psilocybin, the tertiary amine group is on the right hand side of the molecule, highlighted in yellow. In this amine, uh, we have nitrogen connected to connected to 3 alkyl group. The other amine group in psilocybin is this one is secondary, and the amine group which is highlighted in yellow is a tertiary amine group. Explain why this compound is classified as an alkaloid. Psilocybin is an alkaloid because it does contain amine functional groups and it is obtained from plant sources, hence it is classified as an alkaloid. Just like ammonia, amines are also weak organic bases. In chapter number 9, we learn about acids and bases, and according to Bronston and Lowry definition of acids and bases, a substance which donates a proton is classified as an acid. On the other hand, if a substance accepts a proton, then it will be classified as a base. A reaction of ammonia and a water is shown here. The analogous reaction between amine and water can also be written similar to this reaction. For example, for methylamine and water, the products will be similar to the products of ammonia and water reaction. Both of these reactions are reversible and they favor reactant, which makes both ammonia as well as amines weak electrolytes, and it also makes them weak bases. Because amines are bases, therefore they react with acid in acid-base neutralization reaction to form amine salts. An example of acid-base neutralization reaction between ammonia and hydrochloric acid is shown here. We can also write similar reaction between an amine and HCl as shown here. The product of this acid-base neutralization reaction between an amine and an acid is known as an amine salt. If the acid used is the hydrochloric acid, then the product is known as uh, amine hydrogen chloride. Amine salts are more soluble in water than neutral amines, therefore, they are a preferred form for pharmaceuticals. The higher water solubility allows them to dissolve in bloodstream and uh, get distributed more readily through the circulatory system. These water soluble amine salts can be prepared from the neutral amines and the appropriate acid in neutralization reaction. For example, the decongestant ephedrine is produced as its amine hydrochloride salt by reaction of the neutral amine as shown here with hydrochloric acid, forming the positively charged ephedrine cation and chloride anion. This compound is referred to as ephedrine hydrochloride salt, and it is a common decongestant. Let's solve this problem. In this problem, we need to write the product of the neutralization reaction, and then we need to label the amine, the acid, and the amine salt. The product of this acid-base neutralization reaction will be an amine salt in which the nitrogen atom has the positive charge and one additional hydrogen because proton will be donated from the acid to the base, which is our amine. The name of this amine is dimethylamine because it contains two methyl groups on connected to the nitrogen atom. The name of acid is hydrobromic acid, and the name of amine salt is dimethylamine hydrobromide salt. Let's recall all the functional groups learned in this chapter. First, let's recall the functional groups which contain only carbon atoms, and these are alkenes, alkynes, and aromatic hydrocarbons. In alkenes, we have carbon-carbon double bonds. In alkynes, we have carbon-carbon triple bond. Aromatic hydrocarbons are those functional groups which contain an aromatic ring, which is a benzene ring. Alcohols are those functional groups in which a hydroxyl group is present. Hydroxyl group is OH functional group. Alcohols are classified as primary, secondary, and tertiary alcohols if the carbon atom which is linked to the hydroxyl group is also connected to one carbon. Then it would be primary. If it is connected to two carbon, then secondary, and if it connected to three carbons, then it's tertiary. Phenol functional group is similar to alcohol, but the hydroxyl group is connected to the aromatic ring. So this together uh, with aromatic ring and hydroxyl group, it's known as a phenol functional group. Thiol is similar to alcohol, but oxygen is replaced with sulfur. Ether has an oxygen atom linked to alkyl chains or cyclic rings or aromatic rings on both sides. And finally, we have amines, in which nitrogen atom is either connected to one alkyl group, then it's primary. If it's connected to two alkyl groups, then it's a secondary amine. And if nitrogen is connected to three alkyl groups, then it's tertiary amine. With that, we conclude chapter number 11. Thank you everyone for watching the video. If you have any question, please let me know. Have a wonderful rest of the day.